So, yep. So I'm gonna kind of go a bit fast because there's a lot of content. There's a lot of like words in there that has like a lot of meanings to each of those words. So I try to be brief, but I try to kind of go fast as well. And like if there's any question, feel free to raise, and we'll try to get those because we only have like 40 minutes, I think, for the entire presentation. So the whole idea of this presentation is to kind of go over and see how we can secure, basically improve the security on IoT devices. So I'm going to talk kind of, this is the agenda. I'm going to discuss a bit of the IoT needs on the security side, talk about hardware secure modules, and how we like proposed a solution that can use OTA to in the ARM TrustZone to secure the keys used by the device. So when you talk about like the general security needs for IoT, they're usually, like broadly speaking, two blocks of like, like security concerns. One is like for the device itself, to make sure that you're running the firmware that it was supposed to be running there, and it is the authentic firmware as well. So for example, this involves like a secure boot, verified boot, and so on and so forth. And something that is quite already common and usual on embedded devices. So people have been doing that like for several years already, and which is why it's not going to be like the focus of the presentation itself. There's quite a lot of material out there to show how you can do like secure boot and so on. The focus of this presentation is going to be on the second block, that which is basically the network security as we involve like an IoT device. An IoT device is basically, like a traditional embedded device, but it's connected online, like to and send communication to cloud servers. It can be updated over the air as well over the network. So you also have to not only secure the software that is running there, but you have to secure the communication that happens inside the device. So for example, when a sensor is pushing data to the cloud, when it's getting data from the cloud itself, when it's performing the update, you also need to make sure that you're able to protect the communication. And when you talk about like protection, you talk about encryption by default. And when you talk about encryption, you talk about like the managing the keys for the encryption. And when you have like, for example, in IoT, which is pretty common, you want to have like a way to identify the device, and as a consequence, like in a unique way to identify the device. And as a consequence, each device would have a unique key. And that key would need, of course, like to be made available as part of the device. So you also need to protect not only the communication and so on that happens, but as a consequence, you need to protect the keys. Because if you lose the keys, you lose all the security that it was supposed to be protecting. And and this is not something that is new to the industry nowadays. You see, like, for example, cloud deployment and so on, even personal computing in general. People already kind of, having this sort of concerns. They already have, like, solutions that are, like pretty standard over the, like, that's being used over the past, I don't know, like 10, 15 years. And one of the most, like, common solutions is the hardware security module. I don't know if any of you is already, I know that mostly everyone already, have their own key when signing commits or signing emails, encrypting, and so on and so forth. Who actually uses an external hardware security module to store the keys and manage the keys? So it's unfortunately not that common. But the reason is, of course, like you don't want to have your key online on the device or available on a disk or so on, because it's pretty easy to extract and remove and copy, and then you lose the whole aspect of security there. And a hardware security model is made especially for this purpose, to make a hardware that is harder to tamper with, harder to remove the data, and not only the keys stored at the hardware security module, but also like the crypto operations happens inside the module as well. And you see, like, for example, there's network-based devices that can be connected to network, PCI devices, the more traditional ones that are pretty common nowadays, like USB-based devices. And you see, like, there's several different ways to connect to those devices. And if you look how you more kind of generically access a hardware security module nowadays, you naturally find out about the specification that I wrote in here, which is PKCS 11, which is basically an abstraction that gets created, so you only use that API to perform the encryption, to manage the keys, and so on. And then underneath, doesn't matter if like it's a USB bus or like a PCI network, you only kind of get to touch that interface. Now, to show a little bit more about like PKCS 11 and show the importance of it, the specification itself is a pretty high-level platform-independent API for cryptographic devices in general. I think initially focused on smart keys and smart cards, but nowadays is like pretty generic for hardware security modules as well. It's kind of considered the standard API. There's other ways to to manage and use HSMs, but it's pretty like kind of the standard nowadays, and it's supported by a wide variety of like softwares, like for example OpenSSL, GNU TLS, Wolf, OpenVPN, like all sorts of like security related software usually supports PKCS 11. One other thing about it as well, which is good, since it's being used for quite a few years, there's a great tooling support. There's also like software implementations that you can play with, completely done by software, just to test the API and getting like a handle of the usage in there. And the way that API works is a pretty simple definition of the C-based APIs, an ANSI kind of C-based API, and the data itself is managed in a kind of object-based approach. You have like certificates, keys, private keys, and so on, and kind of having a better description here how it works. Like the API is pretty simple. You have like a fixed set of functions. For example, to initialize a token, get information, generating keys in case you want to generate, for example, a key pair. And of course, like the private key would naturally be stored and only available to the hardware, and you would be able to extract the public key. You want to perform encryption, digest, sign, and so on and so forth. And there's also like a fixed set of parameters per each of those functions, but it's pretty well defined and not too complicated to get a grasp of. And now the data itself, the way it's managed, the way it's stored, is basically kind of in an object way, object approach, basically. You have like the key, and then a key, you have like private key, public key, in case, like it's a symmetric key. You can also have like certificates, and then there's also the other way that they abstract, which is called a mechanism. Is basically, like for example, ECDSA would be a mechanism, RSA would be a mechanism, and with that mechanism in particular, you're allowed to do certain crypto operations, like for example, encrypting, signing, deriving keys, and so on. So you kind of combine the key with the mechanism, and then you can perform a set of crypto operations. So, like going back to the beginning of the presentation and talking, like why security is, of course, like critically important for IoT. And you see that there's already, like pretty common industry using hardware, like secure modules for enterprise. And then, of course, like the question is, why can't we just simply use that for IoT, right? It's already there, like there's already great support, API, hardware, and so on and so forth. But then, of course, you end up like the major blocker, which is cost. Like several IoT devices are cost constrained, right? You don't want to have, for example, a lamp, a smart lamp that like costs $200 just because it's secure. Like makes no sense. You're not going to be able to sell, like in the end. So you have, like the cost constraining aspect of it. You could, for example, use TPMs, which are cheap. The hardware itself is pretty cheap, but it's pretty complex on the software side otherwise. So there's still the nice thing is that I think over the past 2 years, like there's been a lot of work on the software side to make it easier, like from the bootloader to the user space and so on and so forth. But it's still like known to be super complex to deal with. The other complicated aspect for IoT kind of in particular, mostly because like once you ship a product, you need to support that product for many years, and sometimes it's pretty hard to replace the hardware in case you have an issue. What you see is that most of those like HSMs, they all have like proprietary implementations internally. Like there is a proprietary firmware that runs underneath, and you can have issues. Of course, you can have bugs, and you can also you end up being blocked by the module maintainer in case there is a vulnerability in there that you need to fix. It's your product, it's your risk, but you're still dependent on the vendor to provide the fix, and sometimes even replace the hardware. So it's not necessarily an easy solution. And the nice thing about IoT in general, at least now currently, is most of the devices that are out there are ARM-based in a way. I don't have the percentage, but I'm sure a large amount is ARM-based. And if you see, ARM, there's several extensions to support all sorts of stuffs. So maybe can we leverage the security extensions, for example, to kind of implement, have kind of the same things as you wouldn't naturally have with an HSM, but supported by hardware. That's something that we started to question as we started to investigate how to best use this. And one nice thing about ARM is that there's a pretty well-defined extension which is called a trusted execution environment, like ARM TrustZone, which basically allows the execution of a secure OS in parallel to the traditional OS. And if you see nowadays, for example, several products are actually already using that. For example, phones like Android phones, set-top box, like the way that they handle, for example, DRM keys, or encryption for the disk on the phone. So they're all using that already. It's just not widely, known and common for people to, to use. So then the question, can we kind of leverage that and have, an HSM implementation that is actually just leveraging what is already on the hardware instead of, relying on another entity. By working in Linaro before, and being involved kind of in the beginning, not participating much, but seeing what happened there. There's now an open source OS that can be run as the secure OS. So the nice thing is, not only, of course, we can change, we can create applications and so on and so forth, but we can start using those extensions in an open source way, right? Which is pretty cool. And here, just kind of to give an overview of how it works. The OTA part in there is just simply the secure OS. The rich OS here is just Linux. And the way that you would use is that you would have your rich OS for whatever that is doing in there. There's a well-defined API, which is part of another specification called a global platform, that talks to the kernel. The kernel now has a TE driver, and that's something that is pretty nice nowadays, is that the OTA TE driver is already mainline, so there's really not much that you can do, that you need to do in order to use it. It's all there. And what that kernel would do is that it would call the secure monitor calls, which would be transferred in a way to the secure OS. And on the secure OS, you can of course perform all sorts of secure related stuff, like for example DRM, which would be controlling DRM keys, how it's used on set-top box, and so on and so forth. So if you see this, it kind of matches well with the needs for an HSM, because what we have here is all the key, all the crypto related, all the secure stuff is completely isolated on another OS. It's still running on the same hardware, but running on another OS. And you can have an abstracted and a specified API to access through your Linux application. So a bit more about OTA. As I said, it's an open source trusted execution environment OS maintained by Linaro. There's several other vendors as well that are working and supporting and sending patches these days from all sorts of companies. NXP, Swan, ARM, quite a few others. The way that it was constructed is basically using the global platform APIs. Global platform APIs is another consortium like that defines what like would be the APIs for trusted execution environments, not only TrustZone, but all like because we also have others, other solutions as well that are similar. And there's basically two main pieces. One is the client API, which is how Linux communicates to the other side, which is a trusted application. In a well-defined API that exposes basically a command ID and up to 4 parameters. And you can also like share a memory between them. So with those command IDs, you can basically implement everything. It's up to you. You can implement your own trusted application, define a set of command IDs, and use those through this API. And on the internal side of things, which is mainly available for the trusted application, there's another set of APIs that can manage, like, for example, trust storage, data, keys, crypto-related calls as well, time, mathematical operations. So basically everything that, like, that you would need in case you would be thinking on the HSM is already kind of available here. So, like, why not just simply leverage that? And just kind of to show, to get a kind of a better grasp on the client API, how it works. Here's like it's your Linux application, how it would be calling the secure application on the other side. As I said, like it's just like an invoke command that would call the secure monitor call, that would process and send the command IDs and the operation. The operation is where it defines all the parameters that are required, and of course like a session, because you need to open a session and so on and so forth to the secure OS. And so we were like investigating how we could, like use HSM on a TrustZone and so on. And we gladly found out that this was something that already started the Linaro. So it was started by the Etienne Carrier. I don't know how to pronounce it. I think it's French. Carrier maybe. But there's an RFC available. It's still not merged upstream, but there's quite a bit of work going. So for anyone that is interested in, like just checking or like going there to the pull request and see, there's also quite a few things missing in case you guys are interested on helping. And the secure key service is not as any, like a secure application is done is like you have the user space side, which basically uses that API that I showed on the previous slide. Here, what we call is like libsks. In this case, that libsks basically implements the PKCS 11 interface. So it's just kind of like maps. It uses the TE command line client API and implements the PKCS 11 interface on top. And on the secure side, there's an SKS trusted application which basically implements the HSM side of things, like all the crypto operations, the key management, the data, and so on, including secure storage, is done by the trusted application. We also, like at Founders, because since this is not yet upstream, we also have like a Git repo containing not only what is on that pull request, but also some other additions that we did and improvements, which we're of course like on upstreaming kind of, to the maintainer first, and then which will land on the project later on. But in case you want to have access to both the library and the trusted application. And as I kind of was showing how PKCS 11 works and how, like the command ID works when you're talking with a trusted application, the mapping and the way that secure key services API works is pretty simple actually. Like for every PKCS 11 call, we simply map to a command ID, and the parameters are passed over like TE command parameters, and in case there's a need for more data or additional parameters, for example, which are not covered on that 4, it's shared memory is used and serialization basically of the arguments back and forth on both sides. And kind of to give a better overview of how we would actually use all of this that I was talking kind of in a real world situation. So the secure world, which is running on the TrustZone, running OpT, which is open source, running as the secure OS. You would have like the trusted application, which kind of implements the HSM running on the secure word. The communication, as I said, like happens through the Linux kernel. It uses the TE client API. Like the maps, the command ID, and so on. And here's the part that was also developed together with the key service, which basically implements the PKCS 11 API to do all of this abstraction. And from here on, it's basically generic, right? It's as any other HSM that you have out there. You would use, for example, OpenSSL, and it's just a matter of using the OpenSSL PKCS 11 engine, and then everything would be transparent, and it would simply behave as an HSM. And like thinking on the IoT, this can be used, like to send data application to the cloud in case you have like a certificate or like a device-specific key that you want to sign information. You can do that. And you can also like secure the update mechanism through the same way, right? Simply by using HTTPS on when downloading the image. And I knew I wouldn't have a way to demo, but I don't know, like super clear, but you can gather the slides later on, or I can demo on my own computer. Here's basically demonstrating how it works. The nice thing is that for KeyEmu ARM64, there's support not only for running the OS, but there's also support for running the secure OS emulated as well. So the way that I call the KeyEmu, I just pass the image, pass the ARM trusted firmware, the OTA as well, Uboot, and so on and so forth. And I open like basically two serials. The first one is the normal serial that you would have, like for Uboot, kernel, and so on. And the second serial is basically the output from the secure OS. So you can, like as you debug, like for example here, OTA version 3.6 and so on and so forth. So you can communicate and you can see what's happening on both sides of the word, to put it that way. And to show how our OTA client actualizer uses this, it simply just uses OpenSSL with the PKCS 11 engine. Like here's nothing was customized. Here's just like the generic engine, talking over like the SKS client library that communicates with the secure word on a trusted application. And here's just sending data, the sign-in manifest, and so on. And you can also see, for example, here the signing taking in place. Like in this case, I have a device-specific key that is maintained in the TrustZone. And when I'm communicating with the server, our OTA client is communicating with the server. It's signing to establish like the handshake, the TLS handshake. And you can actually see the signing operation happening here, like the ECDSA sign with the command, and so on and so forth, proving that the actual crypto calls and operations are happening on the secure OS. So while, as I was showing on the KeyEmu screens, like while of course like most of it is working, there's still quite a bit of work. The next steps, of course, like as we make it its way like on the upstream, it's then testing, like, so we can make sure that we test all the supported mechanisms and so on in the proper way. Additional mechanisms as well. This is something that maps with the PKCS 11 3.0 specification, which should be coming out, I don't know, like in the next few months, which adds basically a new set of like mechanism or crypto operations, different crypto types, and put that way, additional curves and so on. So this is also something that that needs to be done. And as I said, like it's quite a lot of content, quite a lot of individual pieces. The OTA documentation, they updated last year, and now it's all like in read the docs, and it's a pretty extensive documentation, pretty nice to read, get to learn as well how the secure OS works, how you like implement it and create a trusted application. There's several useful presentations. Most of them, I think, were done in Linaro Connect, and including one when Etienne introduced HKS. And so, I would suggest anyone that is interested to take a look at those. The spec itself, if you want to see more about how the mechanisms, which mechanisms are supported, and so on, just go to the Oasis website. The RFC for basically this work that I was showing, for the HSMs, trusted application and library, is on GitHub. So we're still working to get the needed features there and support. And Actualizer, which is our OTA client, also there's a pretty nice set of documentation showing how to use PKCS 11 together with OPT, together with OpenSSL, in order to perform secure communication over HTTPS. And that's pretty much it. So I'll put that here just to have kind of a better picture. Any questions? There's a lot of content.
So basically, IoT, there's some devices that are very, very limited. So, and if I remember correctly, this is for ARM-based architecture.
ARM-based architectures, yes. It ranges from several different, not for example, I know that ARM is introducing now, for example, for MCUs, some sort of TrustZone as well. But for microcontrollers, they don't necessarily have. But ARM v5, I think, already had it. 6, 7, of course, and v8, they all have the extensions. So depends a lot on which chip, on which version and revision. But even for MCUs, they are introducing the same thing, basically.
Okay.
Hi. You said that you are following the API from Global Platform on the open source project. I'd like to know if you are aware of some kind of certification following the common criteria TE protection profile for the open source project.
Yeah, that's actually an interesting question, and I wanted to kind of raise with the maintainers because I don't know how the certification process is happening, if any, at this point. I know they were interested in going and working with that, but I personally don't have information on that. But yeah, it would be needed as well, right?
I hope it's not a really too simple question, but you mentioned at the beginning that both parts can share memory in between. And does this need to be correctly configured to not expose information to each other?
Yeah. The shared memory is more to pass over data for the calls itself that you do, right? For example, I want to encrypt something and I want to send that data, so I populate basically a shared memory with that data and then basically encrypt on the other side. So that's how basically it gets used. But of course, there's several levels of concerns and so on that you need to kind of to handle that properly to avoid mistakes in there. But we try to reduce the use mostly just to pass over the parameters and getting the output basically, and not for much more.
Any more questions? Thank you.
Right. Thank you.